I gave a talk at Balisage a couple of years ago where I started at the beginning of the talk setting off a streaming transformation on, I think it was 15 gigabytes of data, and at the end of the talk it had finished. I'm not going to do that today because I was terrified during the whole talk that it wouldn't finish in time, and everyone was watching to see if it finished rather than watching my talk, and it rather dominated proceedings. What I'll do instead is do a slightly smaller transformation at the beginning, and so we'll get the demonstration out of the way. Let's just look at what we've got here. We've got a file. Can you read that? That's 716 megabytes or megabytes or whatever we're supposed to call them these days. So it's under a gigabyte, but still big enough to really need streaming. And I've got a couple of queries. I'll probably just run one of them. Let's have a little look at the data. Here's the data. It's a protein sequence database, which is in the public domain. And it's got a rather structured introduction for its metadata. And then some stuff which is no doubt fascinating if you're interested in proteins. And I could go on scrolling through that for about 4 days, and we'd get to the end. So I won't do that. What I'll do instead is to, browsing through that kind of data to find what's in it is quite tricky. So one of the things that streaming transformations are quite good at is saying, give me a digest of the data. And very simple transformations can actually be extremely useful on that kind of data simply because there's no other way of finding out what you've got in there. So this might look like a trivial transformation, but it's actually quite useful. And what this one does is it starts off saying, here's a mode and it's streamable. That's saying I want to process this in the default mode for templates is streamable. And there's a new XSLT3 feature there saying on no match equals shallow copy. I mentioned that this morning. That says I don't need to write out the identity template. It's now the default. I'm going to strip space from the elements. That's quite consistent with streaming. I can strip white space while streaming without any trouble. I can indent the output without any trouble. That's all streamable. I've then got one named template to fire things off. And it's just saying XSL stream says apply streamed processing on this URI. And the only thing it's going to do with that URI is apply templates to initially the document node, and then that's going to go through the default templates and apply templates to the children and so on. And then I've got a template rule here that says when I match an element that has more than one ancestor, then kill the processing at that stage, do nothing. So it skips any element at level 2 or more. And if I wanted to drill down a bit, then I could change that number, but then I'd get rather more output. So if I run that in Saxon, it runs. It takes its time about running. You can get some fascinating information while you're watching it. It's better than just sitting watching nothing, so I let it run through. The kind of speed you can expect, I tell people, is about 1 gigabyte per minute. This is a little bit faster because it's such a simple transformation. A more complex transformation might take a bit more. And obviously it depends on the machine, but about 1 gigabyte a minute is what I reckon is sort of par for the course. And that's, you can see it's taken 28 seconds to process that 700 and whatever it was megabytes, so it's running a little bit more than 1 gigabyte per second. And it's telling me how much memory it's used, which in this case is 38 megabytes. So you can see it's very substantially less than the size of the document. And I'm not going to prove it, but that's actually a constant memory. It doesn't increase as the size of the document increases. So that's just a little illustration to show you that this stuff is actually real. So having had this sort of teaser, let's now start the presentation. And this is primarily about implementation. I've got a little bit of background on the specification side, but I can probably skip through that quickly because we've already had a lot of information. I'm going to concentrate on streamed templates. There are more than one way of doing streaming processing in XSLT, but the traditional recursive descent style with streaming templates is available, and it's very often the best way of doing streaming. And Abel has given you similar rules about what your streaming templates must conform to. Here are a couple of examples which I'll introduce because I'm using them. They're both streamable. The first one matches sections. It outputs a div element, then outputs an H3 element. That H3 element doesn't do a downward selection, it's just selecting an attribute, so that's okay. Doesn't return the attribute, it atomizes it, so that's okay. Its single downward selection is the XSLPly templates call. The second one, again, it's only doing one downwards call. We're allowed to get attributes of ancestors, that's no problem. Its single downwards call is XSL value of select equals dot, and that's consuming the entire input tree underneath the title, so we've got to be careful about any other selections that need access to that tree. But they're both streamable templates. Now, a little bit about the internals of an XSLT processor. The classic way, back in XSLT 1.0 days, that you built an XSLT processor was with a little pipeline like this. You start off typically with a push parser. So that guy's pushing. The parser is pushing data onto a tree that it's building. And that's a real tree that lives in memory, a source tree structure whose size is typically sort of 5 to 10 times the size of the raw XML that the parser is producing. It's 5 times if you're lucky, it's 10 times if you use the DOM. Then what happens is that the XSLT transformer, it really, in 1.0, the simpler processors, they have an XPath engine and they have an XSLT engine, and they're separate from each other. And the XPath engine is used to read data from the tree, and pretty well all access to the source tree is via XPath. And that XPath processor is pulling data from the tree as required. It's reading from the tree. And then the transformer is writing to the result tree. The XSLT 1.0 spec even used that terminology. It talked about instructions like XSL element writing to the result tree. That terminology changed in 2.0. It talked about it returning a node. But the model of writing to the result tree was there in the spec and in the typical implementations. But the result tree didn't actually exist in most implementations because the language constrains you to write things to the result tree in the right order, and therefore if you're serializing, it can pump straight through to the serializer. There's no actually point in building the result tree in memory. You've got 2 push processes there, and the tree in between is a sort of virtual tree that never actually materializes itself. So that's the sort of classic simplified architecture of a 1.0 processor. It gets a bit more complicated in 2.0. Firstly, you can add validation at several points in the chain. You can validate the input, you can validate the result. Validators are often streamable push processors. So the fact that you're validating doesn't itself interrupt the pipeline, because you can tag validation onto the back of a push parser and put a validation in between the parser and the source tree. You can put a validator in between the result tree instructions and the serializer without interrupting that pipeline. The guys who developed XML schema carefully did it so that validation could be pipelined in that way, and that's something we're now able to take advantage of. The other thing XSLT2 added was the ability to create temporary trees, and that also works in the same way. You can push data onto the temporary tree. A temporary tree in an XSL variable is typically a real tree in memory. It doesn't have to be always. Sometimes you can optimize it away. But in many cases, the temporary tree is a real tree in memory. You push data onto it, and you pull data off it with XPath. And all of this is in push mode, except for this guy here, who's rather red and embarrassed because he's pulling the wrong way. And that's the thing that stops you pipelining, the fact that that one component of the system is in the wrong direction. Because that means you need to accumulate the data in memory, build the source tree for real, because you've got two separate processes, one pushing and one pulling. Now, my first efforts at streaming in Saxon were quite a long time ago. And I started doing it with an extension to XSL copy of, and then with a Saxon stream extension, which is still very much there, though it's now sort of playing second fiddle to the real facilities that are defined in the XSLT 3 spec. And the way those facilities worked is the XML parser was still pushing, and the XPath processor was still pulling. And I avoided the need to construct a tree in between by having two threads. So the parser was building an element at a time. You had to, obviously, the instruction says which elements you're interested in. Like I want to stream all the employee elements. And the XPath parser will build an employee element, put it in a buffer in memory. The XPath processor will then pull off that item in a separate thread. And the memory is bounded by the size of one employee element. So that sort of works for a particular style of processing and proved quite useful for a class of applications, which is useful, but certainly doesn't solve the whole problem. And in particular, it doesn't solve the kind of applications where you need to do recursive descent and apply template matching to the whole document. So the way the architecture has evolved now is to re-implement the XPath engine in push mode. And I'll say more about what that actually involves. So it's push processing from start to finish, which means you no longer need separate threads. It can all happen in a single thread. And one of the interesting things about that push pipeline is it can work at different levels of granularity. So you can either be pushing individual events. Here's a start element, here's a text node, here's an end element, here's a comment, here's a processing instruction. Or you can push complete items, like the employees. You can still do that one. You can build a subtree for an employee and push that as a single item down your pipeline. I call them composed pipelines, where you're pushing entire structures, and decomposed pipelines, where you're pushing individual events. And at one time, you had to do one or the other, but the way it's evolved now is that you can actually, it's actually a composite pipeline that can actually handle a mixture of the two, which you sometimes need, which actually simplifies the whole architecture. And so it's now a single thread. So this is what it looks like. This embarrassed guy in red has switched around to push along with the rest of the guys, and the XPath processor has been replaced by a streaming XPath processor, and apart from that, there's no substantive change. So the XPath engine is completely rewritten, but other things haven't changed too much. I use this term inversion, and that word comes from Jackson structured programming. Jackson did a lot of work on programming methodology in the 1970s when people were still using magnetic tapes. And when you think about, I'm sure you often think about how you do processing with magnetic tapes, but what you're doing is you're taking hierarchical, in COBOL files are hierarchically structured files, and you're doing batch processing to turn them into other hierarchically structured files. And because you haven't got very much space in your memory, like only about 128 KB, you have to try and stream that processing as well as you can and buffer it through magnetic tapes, and you want to minimize the number of tape operations you're doing. So Jackson was talking about a methodology for transforming hierarchies into hierarchies using minimal memory and streaming the processing as much as possible. So it's well worth going back to that stuff rather than reinventing it all. And one of the concepts that came out of this was this concept of inversion, which is translating top-down processes or pull processes into bottom-up or push processes. And that's what we're really doing here. We're implementing the XPath engine as a push process, as an event-driven process, rather than as a pull process. Not too dissimilar from push and pull at the XSLT level, where we talk about using template rules versus using for each. Template rules is an event-driven model where you say, when something happens, do this, whereas the for each model is a read the next thing and then process it this way sort of model. And it's also similar to the relationship between a top-down parser and a bottom-up parser. A top-down parser is sort of recursively saying, read the next input, do this with it. A bottom-up parser is saying, when I get the next token, this is what rule to match. So it's a concept that applies across a lot of different areas of computing. Here's an example of the count function implemented bottom-up. We have a little, I never know what to call a thing on a pipeline. Internally in Saxon it's called a feed. So a push pipeline consists of a sequence of feeds connected together. And the feed has basically three methods: open, process item, and close. Open is called at the beginning. It opens the next feed along in the pipeline, and it sets a counter to 0. And then each item that comes along, it increments the counter. That's straightforward enough. And then when we close, saying we're finished, we've done that operation, it passes the value of the counter to the next feed along in the pipeline, and then issues a close on the next stage. So that's a simple example of count, a very simple operation implemented bottom-up rather than top-down. Another way of illustrating this, push components, the control flow and the data flow work the same way. So the control flow comes from the person supplying the data, whereas a pull component, the control flow and the data flow work in opposite directions. The person controlling the data is the consumer of the data rather than the supplier of the data. Here's another example, another function implemented bottom-up, the remove function. And the interesting thing that's different about this is that remove takes two arguments. One is the sequence from which you want to remove an item, and the other argument tells you which item to remove. So let's assume that it's the sequence that you want to remove something from that is the streamed input. There's another argument, and you have to evaluate that in the conventional way. So that call of evaluate evaluates the second argument of remove in a conventional pull style evaluation. So we still need the pull engine to do that. We're not evaluating everything in streaming mode because there are lots of inputs and only one of them is streamed. The others are evaluated in the traditional way. So that's how evaluating the remove argument. And then the process item just says if the position of the item is equal to the thing we want to remove, then do nothing. Otherwise, pass it on down the chain. Those examples were both working at the level of items, but sometimes the pipeline needs to work at the level of events. And a common case for that is with what the spec calls inspection constructs, which are basically things that we can evaluate when we're positioned on the start tag without consuming any input. And typically there, the relevant feed for that does the evaluation when it sees the start tag. So there's a start element event, similar to a Sax start element event, except that it supplies all the data, all the attributes, and all the ancestors on a single call. The start element here event gets the name of the element that it's been passed, and it passes that on to the next guy down the chain, and that's fairly straightforward. Absorption constructs are a bit more complicated. What absorption does is to say, read the whole subtree underneath where I am. So data and string and XSL value all fall into that category. But they essentially follow the same kind of model. Here's the string function. When you start, you initialize a buffer. When an item comes in, you say if it's a text node, then add it to the buffer. If it's not a text node, then it's not going to contribute to the string value, so you can ignore it. But this time I need to process all the nodes at every level of depth within that subtree. You can also emit events as distinct from whole items. So if you're constructing a new element, then the feed for that will call start element on the next guy down, start element and end element. So you can actually create a sort of fine-grained pipeline of the things from a coarse-grained sequence of items as well. It works both ways, which is why it's now a sort of multi-granularity pipeline. To make this work, you have to take the expression tree that comes from compiling the source. That builds an expression tree something like this. And then you have to identify what in Saxon is called the streaming route through it. And the streaming route basically consists of all the expressions that in the W3C spec are identified as consuming. So you find the things labeled as consuming by the streamability analysis, and those turn into a push route through the tree. So these bright green things, they are working in push mode on data that's supplied bottom up. You can visualize what bottom up means in terms of that tree. When it gets to this level, it needs some extra data, and that's evaluated top down to supply that data at the right point in the processing chain. So just a summary of how that all works. Everything's the same except the XPath engine. The XPath engine has to be able to evaluate any sequence-valued construct in push mode. Fortunately, a lot of constructs aren't sequence-valued, and things that are, arguments that are just simple atomic values, arithmetic doesn't change because the same logic is used for arithmetic whether you're in pull or push mode because there are no sequences involved. But as soon as sequences are involved, you need a push mode implementation of the construct. And it turns out that the classification in the spec for how you classify expressions and work out whether they're streamable or not is useful not only for getting that binary decision, is this guaranteed streamable or isn't it, but those properties that you've computed are also very useful in deciding how to assemble this push pipeline that you're actually going to use at runtime for the evaluation. So that's it. Thank you very much.
Well, are there any questions? We have time for questions. Yeah, over there. Just wait for a mic, please.
Yes, you mentioned the count function, and I wondered if you could do, how much aggregation can you do on the streaming pipeline?
All the aggregation functions like sum and max and distinct values, they're all streamable. So yeah, a lot of use cases are based on doing simple aggregation, and those use cases work very nicely. One complexity is if you want to calculate two results on the same streamed pass. If you want to calculate both the max and the min, it gets a bit more complicated. And there are various solutions there. One is to use XSL fork, as Abel described, which gives you two parallel evaluations of the same stream. Another process is to use iterator or accumulators that again calculate multiple results in a map. So there are workarounds for more complex aggregations.
Jonathan?
Yeah, I'm trying to get a feeling for how this kind of performance compares to other things. So let me toss out a handful of questions that I have no real knowledge on. I've never done any streaming with XSLT. I've used other things for that. I found a VLDB paper, Dr. Google, quick lookup of something that may not compare at all that claims real fast performance with XQuery. I know people have done things like this with non-streaming XSLT processors. I'm trying to get a feeling for how does this streaming compare in performance to a non-streaming XSLT processor, to standard XQuery processors, to highly optimized, et cetera?
One of my users sent some feedback recently that streaming was about 1.2 or 1.3 times the time for non-streaming. And that figure didn't surprise me in the slightest, because it's optimized a lot less at the moment, and there's a lot of scope for getting it down to 1. I don't think there's any scope for getting it better than 1. For simple streamed transformations, in fact, for any simple transformation, performance is dominated by parsing speed. So we can't be faster than the parser, except in one particular case. And that's if you only want to get some data from the beginning of the file, we can abandon parsing after reading that data. And in that case, it's a lot faster than building the whole tree. But apart from that special case where you're only looking at the beginning of the file, it will never be faster than the parser, and it will be a bit slower depending how much transformation work you're doing. But that creates an upper bound on the speed.
Thank you. Is there anyone else?
To what extent can you leverage schema information to optimize here?
Schema information isn't used in the W3C spec for the streamability analysis currently, and it's not used by Saxon for the streamability analysis except in some very simple cases. It can be used to decide that things are streamable that wouldn't otherwise be. That's certainly a prospect. Using it to speed up performance, I haven't found many opportunities there.
Thank you very much, Michael.
Okay, thank you.